Hello guys, today we're going to take a look at the vector analysis required in the electrodynamics. So the first one we're going to take a look at is Kronecker delta, and here is a symbol invented by Einstein, and this is basically epsilon ijk when ijk is in the arrangement of 1 to 3. 312 and 231, it is going to 1. For example, for epsilon 1 to 3, it is equal to 1. And when ijk is in the arrangement of 213, 321, and 132, it is going to be negative 1. When ijk is in different arrangement, for example, like epsilon 113, it is going to be 0. And the second one we're going to take a look at is delta ij. And when I is equal to j, this is equal to 1. When I is not equal to j, it is going to be equal to 0. So for example, delta 1, 2 is equal to 0 and delta 2, 2 is equal to 1. Okay, moving on, we're going to take a look at this and why it is equivalent. So for the case of 1 to 3, 3, 1, 2, 2, 3, 1, and we can see that like this kind of matrix is going to be 1. And when 3, 1, 2, this is also going to be 1. And 2, 3, 1, this is going to be 1. And when it is in the arrangement of 1, 2, 1, 3, negative 1, and 3, 2, 1 is negative 1, and 1, 3, 2 is negative 1. So, and the rest is just equal to 0. For example, when it is like this, it's going to be 0. So we can see that like epsilon 1 ijk is equivalent to this form. And you kind of need to remember this. And going on, we're going to take a look at this and what it is equal to. So you actually need to know a theorem, and it is the matrix A like times B is equal to the determinant of A times determinant of B. And for this proof, just check out the video by 3 Blue 1 Brown. And it is in the essence of linear algebra. And the video is about determinant. There's a proof at the end. It's kind of a proof, but not really. Yeah, I guess it is. I don't know. And there's also a property called A transpose is equal to A. And for this proof, just prove it by yourself or just search it out. So for this, it is going to be equal to the determinant of epsilon I1, I2, I3, J1, J2, J3, K1, K2, K3, and times, like, we're taking the transpose of this one. So it is going to be like L1, L2, L3, and this is hard. I suck at this stuff. And M2, N3, and taking the transpose, M3, N. Oh wait, is it 2? I kind of forgot. Just write it out. Oh my god. So this one is equal to L1, L2, L3, M1, M2, M3, N1, and 2, and 3. And taking the transpose, you just here to here, and here to here, and 1, and 2, and 3, and 3, and 2, and this one is L3, and 1. Here we go. So if we take a look, just this stuff, if we just take a look at this stuff, so what is going to be equal to? So when you time it, it is actually equal to J1 N1 plus J2 N2 plus G3 N3. So you can see that the case when this is equal to 1 is when J is equal to 1, because J is choosing from 1 to 3, and N is also choosing from 1 to 3. So if J and N both equal to 1 or 2 or 3, this is going to be 1. In other cases, if J is not equal to N, this is just going to be 0. So you can see that this form is equivalent to the form of the first IL and this IM and IN, GL, GM, JN, KL, KM, KN. This is a very, very nice property, and we're going to use it to prove what this is equal to. And before doing that, we're going back to A cross B and why this is equivalent. If you write out IJK, AI, AJ, AK, BI, BJ, BK, so this is equal to like this times this minus this times this, and write out, you can see the term is equivalent. Just prove it by yourself. It's quite simple, to be honest. I'm going to erase this. And now we're going to see, because like this is kind of similar to LMN. So in this case, L is equal to K, and M is equal to L, and N is equal to M. So this form is equal to IJK. Oh my god. So in this case, let me move this to here. So IK, JK, KK, and this is IM, M, IL, IM, GL, KL, JM, KM, and this is equal to, this term is equal to 1, and if we move it up from here to here, and there's also a theorem for that, like if you move it to here, they're just equal to each other. IM, JK, GL, JM. So, and this term is equal to 1. And this because they are not equal to each other, so this term is equal to 0, and this one is 0. So basically, it leaves out the form of 1, IL, JM, IM, JL, 0, 0, blah blah blah. We don't care about this. So this is equal to IL, JM minus IM, JL. This is really, really important. Okay, you should remember this. Let's put in here. Okay. Okay, there's also like theorem, which says KLM is equal to LMK. It just moving this to here and this to here, just 2 steps. When the like letters moving like 2 steps, it just equal to the original. And when you take 1 step, for example, like KLM, you move K to L, or you switch K to L, which is LKM is equal to the negative of this. Okay, for now we're going to take a look at this. So if we and phi and these 2 terms are just like scalar, they're not vectors. So if we write gradient in the form of this, and phi like this, we're just going to check the first term. So by the chain rule, like this is just going to be equal to phi x plus like chain rule by x in the x direction. So you can see that this term are just equal to each other if we going down the list. Okay, moving on to the second one, which is this. So basically, if we write gradient in the form of this, which is dotted with phi and this phi x, fx, fy, fz, this is equal to, by the chain rule, the first term is we are just taking a look at the first term, which is equal to fx, the phi, and the second term is equal to phi x. And going down the list, we can see that this is just equal to this f. Oh wait, there's no x. Oh my god. And it is plus, and this is basically f dot the gradient of this plus this times the gradient, the divergence of f. And moving on to dot product. For this one, we actually can use like Kronecker delta stuff. And for this, we can write out like, we can treat it as a vector like A, and this one's B. So recalling the fact that this is equal to ijk, like AI, BJ, EK. Did I write it? Yes, I have. Or this, when we switch terms, this is also equal to ijk, like AJ, BK, EI. So, okay, let me move it to this side. This is equal to ijk, J, phi, F, K, EI. So this is equal to ijk. By the chain rule, this is equal to ij, fk, ei, plus ijk. Let me delete this stuff. ijk, and this one is phi k, j, phi ei. And we can see that this is equivalent to the form of this. probably this. I kind of forgot. You can prove it by yourself. It's probably this stuff. Okay, moving on to the next stuff. For this is also pretty good. So when we take the Kronecker delta, so this is going to be EIJK FJ GK EI, and we dot it with we take the divergent, which is basically saying that it just is, okay, because it is dot product. So which is this term is just equal to this IJK I FJ IJK, and this stuff is equal to IJK I IJK, and the second one is just plus GK IJK I FJ, and we can see this is equivalent to G dotted with like F, because IJK I FJ EK is equal to this, and we can see the like K and K, it just basically dot product. Wait a second, let me delete this stuff. So the first one is equal to this stuff, and for the second one, and by the same case, we can see that FJ. If you switch, just see that like IKJ negative FJ I EK. This is equal to the form of this F. This is basically this. So so now we prove the theorem of this. Okay, moving on to the next stuff. The next stuff is harder to prove, but it's okay. Not too bad. So the inside, and we're just going to take a look at the outside for now. So this one's A and this one's B, IJK, J, K, I, and this is the inside, because there must be a K term. So there must be a K term here. So basically, this is equal to the IJK, J, LMK, FLGM. Okay. Just to be clear, there must be a K term, because we take the K factor, okay? So it just basically this form, which is equal to IJK and this term LMK J FLGM EI, and by the theorem on the top here, we can see this term is just equal to ILJM minus IMGL times OJ FLGM EK. And we're going to take a look at the first term, which is equal to LGM times, by the chain rule we can get this is equal to J. It's hard to erase. FL J GM plus GM J FL. So IL GM FL J GM. The first term requires that this is, and don't forget, there's EI, this time EI here. The first term requires J is equal to M, so this term is just equal to each other. So meaning that it is just dot product. And the second term I is equal to L, which requires vector is the same. So this basically is this. And for the second term, which is ILJM J FLEI, and the first term requires that J is equal to M, so they're the same. So J GJ RJ F, and this is the same FIEI. So by we can write it in the form of this. For convenient purposes, okay? For convenient purposes, we write out like this. So this is equal to J dot this F. So what is this? It is just for the F, it is taking that Rx, Gx, Fx plus a y, Fx plus Gz, Z, Fx, and so on. They're equal to each other. Okay, moving on. So the first two term is equal to, okay, so this one is the first, this is the first, and now we're going to take a look at the second one, which is this one. So it is equal to IMJL, and by the chain rule, this is equal to this. FLRJ GM RJ FL EI. Observe the first term is IM JL FL RJ GM EI minus. And the first term required I is equal to M, and this is equal to this. Wait, I am. Wait, it's I am. Never mind. So they're equal to the term. So this I, J, R, J. So by the same meaning, it is equal to F, J, because I is equal to M. So it's basically minus. And the second term is minus IM, JL, GM, JFL, EI. So which requires that they're equal to each other, and the terms are equal to each other. So this is equal to, yeah, I can see. Wait. And G. Okay, here we go. Let me check. Yes, it is correct. So, yeah. For this term, it is just equal to this minus this and minus this. And for, let's move on to a more complicated one, or I think this one is kind of simple. So it's just basically ijk, like we treat this one a, b, of l, lmk, l, m, ek, ei, k, and this is basically equal to ijk, lmk, wait, this one's j, oh my god, what am I doing? J il fm ei. This term is equal to iljm minus imgl. Times g il fm l m j k. Okay, that's fine. Yeah. So the first term basically requires it is jm j l fm ei, which is requiring that I is equal to L, and J is equal to M. So the first one is basically equal to, okay, let me think. Yes, it's basically this. And the second one is minus im gl j ll fm. We can see g is equal to l, f is equal to I. So this term is just basically this, in which this is like equal to this. And dot dot dot. Okay, let's go. Let's go to the hardest one. And the hardest one is 12. 12 is really hard. And 12, okay. Let me see. Yeah, I'm gonna erase all of this. There's no space. Just wait a second. Okay, here we go. So for this one is just equal to, let me see, this one's I, j, bj, I, and which is by the chain rule, bj, I, rj, ei, plus rj, bj, ei. And if we select that, we can see this term is equivalent to the form of iljm bm I rj el. Okay, wait a second, let me see, yes. Because it requires I is equal to L and J is equal to M, and they're just basically equivalent to each other. So moving on, we can see this term, and there's a formula for like ijk, lmk is equal to il J M I M and GL. So this term is equal to IJK LMK plus IM JL. So this IJK LMK and times BJ. Wait, what I'm doing? I J E L. And for the first term, we can group it. ELMK and movie. And this one's moving IJK, I, J, and EL. So now we can see there's a grouping strategy. So, okay. Yes, this one is a K term. So this is basically EK, K term, equal to this. And this is basically like, okay, ELM, K, BM, A, K, which is equal to B cross with this. And for the second term, minus IM JL. And this times BM I JL requires this is equal to this, and this is equal to this, which is we see that many times. This is basically this. So so we can see this term is also very similar, which is equal to this. So basically, this term is equal to this plus this plus this. Okay, we're done with the vector analysis part, and we're going to see the spherical coordinate stuff. And you just need to remember that, like Laplace, like of u is equal to this. Just remember this. And let me draw a graph. It'll be more clear. For R is just like, so how long is this stuff? And theta is just measuring of this. And like this phi is measuring the angle of the projection of this. And for the like spherical coordinate, and like this one's for cone, basically this is equal to this. And moving on to like tensor stuff. So for tensor stuff, AB, like you can call it tensor. This stuff is just basically a matrix, and you can write it out in the form of this. And usually, it's like tensor is like this: 1 1 and 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. Stuff like this. It's just a matrix. Not too complicated. Okay, this one's really easy to prove, and I just want you guys to calculate stuff. This stuff is also really easy. Just you need to take a look at this stuff first, and just use a chain rule for this, and you can see that R is equal to this, and use the chain rule to find the stuff. And the next one is equal. It is, I forgot what it's called. It's like tensor double dot with another tensor is equal to b dot c times a dot d. And here's also stuff like this. Like the last one, you just prove it with this IJK and stuff. This one is also really easy to prove. Okay, we're done with vector analysis. Now, I hope this video is quite helpful.